Hello and welcome to this webinar on identifying performance bottlenecks in hybrid MPI and OpenMP software. My name is Jonathan Boyle and I work at Numerical Algorithms Group, and I'll be co-presenting today with my colleague Judith from the Barcelona Supercomputer Center, and we both work on the POP project. So first of all, a little bit of background, introduction to the problem that we're addressing. I'm sure many of you have already experienced that getting good parallel performance is difficult. Even with the simplest parallelism, we need to start thinking about things like serialization, load balance, memory bottlenecks, processor frequency, whether the instruction count is increasing or not. And then the parallelization will add overheads as well. For example, data communication with MPI and thread synchronization in OpenMP. On top of this, having hybrid code with got MPI and OpenMP adds to the complexity. You then just need to start wondering whether the problem that you have with your code is inside the MPI or the OpenMP. And I'm sure, like me, you've plotted parallel scaling plots to try and work out what's going on when you've written your parallel software. I've got an example here on this slide. These are useful in the sense that they tell us if there's something wrong with the parallel scaling, but they don't actually give us any insight into what's wrong. And there's a fundamental problem as well now when we're typically looking at the scaling of compared to performance on a single compute node. These speed up plots tell us nothing about the parallel performance on one compute node. You've probably got tens of CPU cores on one compute node, and your speed up on that one compute node is always going to be 1. So you don't really know anything about whether the parallel performance on that one node is good or bad. So there are many powerful tools out there which can help us understand parallel performance issues. For example, in POP, we frequently use the Barcelona Supercomputer Center toolset and the Scholastica toolset. And there's other toolsets, other tools out there. For example, Intel provides some quite nice tools, and there's many others. But my experience is that the data they generate is usually quite overwhelming. Typically, you end up with extremely detailed and complex event timelines for every single thread. So you can see exactly what a thread's doing for the entire execution, but there might be hundreds, thousands, hundreds of thousands of events on that timeline. So it's very difficult to actually interpret that and understand where the bottleneck is occurring. And many of these tools provide vast amounts of metrics, and the metrics, they're very useful, but they're often very difficult to understand. So you have to do a lot of reading to actually get to grips with what they mean. And there's often a lot of them. So you actually have to start, you have to start trying to work out which ones you want to look at first. So you end up with this catch-22 situation where you need to start making some kind of sense of the trace data before you know what you're looking for in the trace data. But now, how do we do this? And the solution we've come up with in the POP project is POP metrics. The idea is it's a very easy to understand set of metrics which can be easily calculated from typical trace data. And the metrics will point you at a specific cause of performance bottleneck, which then helps you understand what you need to start looking for in the trace data. This idea has been very successfully demonstrated in the POP project with our MPI metrics. And we're now extending this to hybrid MPI and OpenMP code and beyond. We've got two approaches for hybrid code. Both are based on the POP MPI metrics. The first of these, which I'll be talking about next, will extend the idea of defining an individual metric per source of inefficiency. And the second approach, which Judith will be talking about, extends the multiplicative approach of the POP MPI metrics. So just to give you a flavor of how these metrics work, the POP methodology defines a hierarchy of metrics, and there's a nice online training course on the POP website, which is worth looking at if you're unfamiliar with this approach. And the top level metrics for both of the schemes we're going to be introducing today are identical, and they're the same as POP's MPI metrics. And these top level metrics are parallel efficiency, which tells you how efficient the parallelization is, computational scaling, which tells you if the total useful computation is increasing or decreasing, and global efficiency, which measures the combined inefficiency from the parallelization and computational scaling. And just to show you how simple and easy it is to calculate these metrics, I'm going to define them now. So if we define comp as the time in useful computation on each CPU core, so this is the time spent executing useful user code, and comp ref is that same useful computation on a reference case. The reference case is normally the smallest number of cores used, typically a single compute node. If we assume strong computational scaling, then parallel efficiency is simply the average comp taken over all the cores divided by runtime. The computational scaling is the ratio of the sum of comp ref to the sum of comp on all our other cases under consideration. And global efficiency is the product of these two metrics. And these metrics in themselves are very powerful. It gives you quite a lot of insight into what's going on. It gives you an understanding of your global efficiency and whether the problem arises in the computation or in the parallelization as you increase the number of cores and compute nodes in your parallel execution. So now we're going to be talking about the first method. We refer to this as the POP additive scheme for MPI and OpenMP to differentiate it from the second scheme, which Jude will be talking about, which we call the multiplicative scheme. So to give you a bit of background about where these additive metrics come from, let's revisit POP's parallel efficiency. So this measures the efficiency of the parallelization. So we measure the useful computation and the runtime on n cores. So comp is the useful computation on each CPU core. And parallel efficiency is simply the average of comp divided by the runtime. And we can think of the average value of the useful computation as an ideal runtime. It's essentially the runtime we would get if all the useful work, which is the useful computation, is split evenly over all the cores and there's no overheads from the parallelism. And similarly, if we look at global efficiency is the sum of the useful computation for our reference case divided by the number of cores for all the other cases under consideration, divided by the runtime. So we can think of the sum of the reference computation divided by n as an ideal runtime. It's the runtime we would get if all the work from the reference case, if all the useful work from the reference case is split evenly over n cores with no overheads. So in POP's additive metrics, we want to define some performance bottlenecks that can be mapped to known issues. And for each class of performance bottlenecks, we're going to try and define an ideal runtime. And then for each class of bottleneck, we calculate the efficiency as ideal runtime divided by runtime. And we can also define inefficiency, an inefficiency metric as 1 minus the inefficiency. So for optimal performance, the efficiency is 1 and efficiency is 0. And this can be used to define a hierarchy where we can add the child inefficiency values to get the parent inefficiency value. And it's fairly easy to see this because the inefficiency value is essentially the time cost of the bottlenecks that we're considering divided by the runtime. So if we split the time cost of bottlenecks into individual contributions, we're essentially splitting the inefficiency value. So now to start talking about how we can define some additive metrics for MPI and OpenMP. So we're going to start with parallel efficiency, and we want to split this into child metrics. And with additive metrics, we've got complete freedom about how we define the child metrics. But one obvious option is to split the parallel efficiency into a process efficiency, which ignores all the thread inefficiencies, and a thread efficiency, which ignores all the process inefficiencies. And we're going to define this such that the parallel inefficiency is the sum of the process and the thread inefficiency values. So I don't have time to go through all the metrics today, but I'm going to illustrate this with the case of process efficiency, just so you can get an understanding of how these metrics can be defined. So to assess process efficiency, we essentially want to know how evenly the useful work is distributed over the processes and how much time the processes spend in MPI. And if we ignore the threading, there's only 3 states to think about. A process is either in serial computation on the master thread, so we're going to define this time as serial comp. Alternatively, a process can be inside an OpenMP parallel region, define this time as OMP. And the third state that's possible is a process could be inside MPI and outside OpenMP. So we're ignoring the threading, so we're going to assume that the only the time outside OpenMP and inside MPI is not useful. So basically, serial comp and OMP are our useful times. So useful is serial comp plus OMP. And we can then define an ideal runtime as the average value of useful. And we can define a process efficiency as the average of this over all the processes divided by the runtime. And we can keep turning the handle and using this methodology to churn out additional metrics. So we can split process inefficiency into child metrics, and it's fairly easy to do this to define a load balance efficiency, which measures the imbalance of useful over the processes, a transfer efficiency, which measures the cost of MPI time due to data transfer of the network, and a serialisation efficiency, which measures the remaining time cost inside MPI. And we can continue this process to define a thread efficiency, which measures the cost of the remaining non-useful time once we've considered the process inefficiencies. And we can split this into submetrics. We can define a serial region efficiency, which measures the cost of the computation outside OpenMP when cores will be sitting idle because there's only computation on the master thread. And we can define an OpenMP parallel efficiency, which measures the cost of the time outside useful computation in the OpenMP regions. And we can keep going and split the OpenMP parallel region, sort of the OpenMP parallel efficiency. And there's two obvious ways to do this. We can actually calculate a contribution per OpenMP bottleneck. For example, we could calculate a contribution due to thread load imbalance within the OpenMP parallel regions. Alternatively, we could split the OpenMP parallel efficiency into a contribution per OpenMP parallel region. So then you actually know which parallel region is, which one is most important when it comes to contributions to the inefficiency. So this method then allows us to define a metrics hierarchy where we split parallel efficiency into process and thread efficiency. We split process efficiency into process communication and load balance efficiency, and communication efficiency is split into transfer and serialization efficiency. And thread efficiency is split into serial region efficiency and OpenMP parallel efficiency, and the OpenMP parallel efficiency can be split further. So I'm going to show you how this works for the real example. In this example, I've shown you some data here showing strong scaling with one thread per process on 1, 2, and 4 compute nodes, and I'm showing you wall clock time. So we can immediately see there's something seriously wrong with the parallelization of this code. The wall clock time is actually increasing as we increase the number of compute nodes. And when we're running with multiple threads per process and keeping the total number of threads constant, so every time we double the number of threads, we halve the number of processes, we see something quite interesting, that on a single compute node, the wall clock time goes up as we go from 1 to 2 to 8 threads per process. And for the 2 and 8 threads per process cases, the wall clock time does actually go down then when you run on multiple compute nodes. But we see here very clearly that the optimal runtime is the case where we're running on a single compute node with only 1 thread per process. So what's going on? So here's a table of hot metrics. There's quite a lot of data here. So I'm going to first of all point out that I'm showing the data in columns, where the first 3 columns were showing data on 1 compute node with 1, 2, and 8 threads per process. Total number of threads is 48. And then the next 3 columns are showing 2 compute nodes with 1, 2, and 8 threads per process. And then the last 3 columns are showing the same data for 4 compute nodes. So the first thing we can identify here is what needs investigating further. I've highlighted in yellow here the metrics that are the ones that are concerning. But these metrics are color-coded so that values between 8 and 1 are green. These are the metrics we don't have to worry about. And metrics between 0.8 and 0 become increasingly red. So they're the metrics that are affecting performance. And the first thing I normally do when I look at a table of metrics like this is look at the metrics at the bottom of the tree and see which ones of those are red. We see immediately that the main problem with this code is process transfer efficiency. It's spending far too much time inside MPI data transfer. But there's some additional problems as well. If you look at thread efficiency, we can see that on 8 threads per process, the serial region efficiency is low, particularly for the one compute node case, which means there's too much execution outside OpenMP. And we can also see on the 4 compute node case with 1 thread per process that the computational scaling is low because the instruction scaling is low. So the total number of useful instructions is increasing. So I immediately know that I need to look in the trace data to try and identify where the data transfer is occurring, because that needs fixing. And I also need to try and identify the serial regions and to see if I can put those inside OpenMP parallel regions. And maybe I want to look at the instruction scaling as well. We can also use these metrics to look at trends. So we can look at the single thread issues, which are highlighted in yellow here. So we see on single thread, transfer efficiency is particularly low, and the computational scaling is low because of the instruction scaling. I can look at the single node hybrid performance, and I can see that the global efficiency is dropping. I can see the transfer efficiency gets actually worse on 2 threads per process and then gets slightly better. And I can see the serial region efficiency is getting worse. There's also another interesting effect that's occurring here, and that is the IPC scaling. It's getting better, which means that as I increase the number of threads per process, the number of instructions per cycle is getting higher. So there is some performance benefits that we can identify here from running on multiple threads, as well as the poor performance from the serial region. And all the other metrics are quite high. So we can see that the OpenMP parallel regions are efficient, there's good process load balance, and there's very little serialization to worry about. And we can also look at the, can use the metrics to compare single versus multiple mode hybrid. So for example, I can see on 4 compute nodes that the transfer efficiency actually does improve as I increase the number of threads, although it's still always worse than on a single node. I can see on 4 compute nodes that the serial region efficiency drop isn't as bad. And I can see that on 4 compute nodes that instruction scaling actually gets better as I increase the number of threads. So hopefully I've illustrated how you can use these metrics, how you can calculate your own set of metrics if you want to, and how we calculate the metrics presented here. So now I'm going to pass over to Judith.
Thanks, Jonathan. Good afternoon. I'm going to present a different approach targeting the same goal. So we want to analyze the efficiency of a run for an hybrid code. And as Jonathan said, we want to keep closer to the original model that was developed many years ago. So basically, the first step is directly apply the original model. What does it mean? If we analyze how the metrics at the original model are computed, and some of them were already mentioned by Jonathan, parallel efficiency measures the percentage of time you spend computing. That is what you want to do. And it's split in 2 concepts. Load balance efficiency measures the time work distribution, and is computed as the ratio between the average and the maximum. And communication efficiency measures the weight of the communication in the execution, and is computed as the higher percentage of time computing. As you have seen, the definition of these 3 metrics has nothing specific related, the formulas has nothing specific related to MPI. So I can directly apply to any paradigm, to any version of my code. Let's assume, for example, that I have a pure MPI code that I later parallelize also with OpenMP in an hybrid mode. Applying these metrics, the benefit, there is a clear benefit. I can compute the same metrics for the 2 versions of my code, and I can directly see if the communications of the hybrid version is better or worse than the one for the pure MPI version. So the only difference between the pure MPI version and the hybrid version is that in the hybrid versions, both MPI and OpenMP runtimes are considered the overhead. But as we are computing the metrics based on the computations, the idea is the same. There is a limitation if we limit the analysis to these three metrics. Let's consider I say, okay, my hybrid code has more issues in load balance. The question will be, okay, but that load balance happens in MPI, OpenMP, in both? How do I know that? So the problem is those hybrid load balance and hybrid communication efficiency are in fact combining the contribution of the two programming models underneath. So we need a way to split them. Basically, what we want is to be able not only to classify the power efficiency between the fundamental factors of load balance and communication, but also to split the contribution of each of the parallel programming paradigms that we are using. And if you accept that, as we have seen based on the formulas, load balance and communications are concepts that can be applied to any parallel paradigm or any combination of programming models, we can compute, once we isolate MPI and OpenMP contribution, we can compute its underneath efficiency. So for MPI, I can compute the communication efficiency and the load balance. And as I said before, in the hybrid metrics, I am basically combining the data from the two programming models. So I can also create the relationship between the hybrid metrics and the underneath level. So if we focus on the top and bottom levels of this graph, basically our approach with the multiplicative model is to split the power efficiency over the two main axes of this execution: the fundamental factors that are load balance and communication, and the programming paradigms that are in this case MPI and OpenMP. The intermediate level basically is a way to go through the path. So I can first distinguish between the factors and then split the contribution of each programming model, or I can first look at the contribution of each programming model and then distinguish the contribution on each of the factors for each programming model. I think you may agree with me. This is a nice way to do it, but then the question is, how can I split the contribution of each programming model? When I started to develop this extension to the original model, my first target was considering that MPI is a kind of upper level of the parallelization. I think this is, or at least it was, the most frequent approach. I have, as I mentioned before, I have a pure MPI code. Then I extend the parallelization to OpenMP to reduce the network traffic and to benefit from the higher size of the nodes. And this is the version I have. And what do I mean by this kind of upper level of MPI, that kind of hierarchical code? What I mean basically is that while MPI is only executed by the master threads, and while MPI takes place, all the other threads are either idling, if that happens outside a parallel region, or they are waiting in a barrier, if that happens inside a parallel loop. I am currently working to adapt the formulas to allow more flexible execution, where multiple threads can call to MPI, where some threads may be computing while the MPI takes place. But this is not yet ready, so let's keep on this original hierarchical code that I think still is the more frequent case for many codes. So let me show you how it works within one example. This is a Paraver timeline for the ones that are not familiar with Paraver. This is a timeline I have on the x-axis, I have time. On the y-axis, I have my MPI ranks and my OpenMP threads. And the coloring of this timeline is showing the duration of the computing regions between two consecutive calls to any of the parallel runtimes. And here I mean either MPI or OpenMP. It is displayed as a parallel gradient going from light, that means short, to dark, that means large. And I basically identify two phases. The one on the left corresponds to a large computing phase, colored in dark blue. The one on the right corresponds to a shorter computing phase, colored at kind of light blue. Using those computations, I can compute the metrics at the hybrid level. And the diagnosis is clear. My efficiency is bad, and the reason is load balance. So if I want to isolate MPI, what I need to do first is to look at what is the MPI behavior. If I show the MPI timeline, I can verify that only the master threads are calling to MPI. And I can also see the time in MPI is very small and is very focused and narrow in two phases, between the first and second phase and at the end of the execution. I can even remove from this picture all the threads that do not have any MPI activity. And I can see in this picture the activity of the MPI calls with the processes that call MPI. So I can use this timeline to compute the metrics for the MPI, because basically from the point of view of MPI, the parallel runtime of OpenMP is as useful as the computation because it's outside the control of MPI. So using this picture, I can compute efficiencies. And what it tells me is that can be my guess because of the picture is that the power efficiency at the level of MPI is almost perfect, and both load balance and communications have no problems at all. So from that, I will say, well, if I have a problem of load balance at hybrid level and it does not happen in MPI, that should be OpenMP. And this is the approach I use to compute the OpenMP metric. Basically, I will say that any inefficiency that cannot be justified by MPI, but that is identified at the hybrid level, is caused by OpenMP. So I can compute any of the metrics for OpenMP, dividing the hybrid efficiency by the MPI efficiency. In these examples, and using the numbers of the previous slide, I get the values and I see, well, OpenMP efficiency is low, the power efficiency, and the reason is clearly load balance, as I expected. I can look at the parallel functions to understand what's going on, and I can see there is only activity of parallel functions on the right of the picture, meaning that the first phase was not parallelized with OpenMP. And this is the way this model is reporting the imbalance generated but not parallelized OpenMP regions. Basically, it's reporting that the master threads have much more time working than the slaves because of that phase that wasn't parallelized. Let's look at another example where I have kept the same original phase 1 and I modify phase 2 to generate imbalance between the different MPI processes. If I compute the metrics here, it tells me, yes, you have a huge problem of load balance. Well, a little bit worse than the previous one, but still quite bad load balance. So looking at MPI, just looking at the MPI calls for the MPI processes, I already see a huge amount of time now in MPI, and I see the imbalance between the processes. So the lower my rank is, the higher the time I spend in MPI. Based on that, when I use this picture to compute the metrics, it says, yes, you have an imbalance problem at the level of MPI, between the MPI ranks. If I do the same for the OpenMP, using the previous number you have in this slide, I get the result that it also has a problem of load balance in OpenMP, and as much serious as the one in MPI. Based on the previous example, we know that the first phase had this OpenMP imbalance because it was not parallelized with OpenMP. So we can make the guess that the second phase only have MPI imbalance and there is no additional extra imbalance between the OpenMP threads. And we can verify that. And I use this example to show you a little bit how we can analyze and the powerful of this kind of metrics in a dynamic analysis in a trace. If I refocus my analysis and I focus on the area that is on the yellow box and compute the efficiencies again, now they have improved a little bit, but there is still a huge problem of imbalance. And computing MPI and OpenMP efficiencies, I can see that the problem now is only in MPI and the OpenMP balance is almost perfect. So basically, after this analysis, I can say, yes, I have a problem in my code of imbalance. The imbalance is in both MPI and OpenMP. First phase is OpenMP imbalance. Second phase is MPI imbalance. So this is the kind of procedure I can use when I use the metrics I propose. And you can compute globally for the iterative ratio what is the factor, but then you can apply to different regions, sub-regions of that phase to identify where are the issues of each of the programming models. But if you look on and think how I compute the metrics related with OpenMP, there was nothing at all related specific, again, for OpenMP. My formulas was just dividing the blame that cannot be explained by the MPI. So in that sense, I can apply the same approach to MPI plus CUDA. And in fact, this is the origin of this model. Around 1 year, something more, 1.5 years ago, I have to analyze my first MPI plus CUDA application. And after computing the hybrid metrics, I need some way to split between the different programming models to justify how to dig down this analysis. As Jonathan already presented an analyse table and explained you how to dig down the information on the efficiencies table, I here present the data in a different approach. I use this plot where I only collect 3 of the metrics. Dark blue line corresponds to the global efficiency, yellow line corresponds to the hybrid parallel efficiency, and the green line corresponds to the MPI parallel efficiency. And basically, I am analyzing when I increase the resources of my execution, what is the scaling of my application, the efficiency of the scaling of my application. And you can understand this picture if you consider the area and the gap between the lines. So from the top of the plot until the green line, this is the contribution of the MPI component at the different scales. The area between the yellow and the green line corresponds to the contribution of the CUDA component. And the teeny gap between the yellow line and the blue line corresponds to the scaling of the computations. So automatically you see that the main problem, the huge gap, is in the CUDA component. So the main loss of efficiency is caused by CUDA. Nevertheless, you can see that this gap, the size of this gap, is almost constant along all the scales, meaning despite this, the main problem for the efficiency is not the problem for the scaling limitations. On the other side, if you look at the MPI contribution, with small core counts, the gap was very small, but the distance increases with the scale, meaning the limitations of the scaling is related with the MPI component. That somehow makes sense because this is a strong scaling approach. So you are increasing the number of resources, you are reducing the amount of work per process, and the pressure of the communications increases with the scale. Just to conclude, how you can compute those metrics. If you work with extract data, you can use specific Python tools that we have developed. There is the NACPy tool that compute the additive models, and there is the basic analysis from BSC that compute the multiplicative metrics. So both of them are available for download, and you can use them. If you prefer to work with Scorpy traces, Scalaska and Cube have also support to the pop metrics. I think in the public version, there is already support to some of the metrics, and in the newer version, there will be extended support to the metrics. And in general, if you prefer another tracing tool, you can also use the metrics that you can calculate manually. You have details on these slides, you have details on the handout that we distribute with the webinar. But also POP can do it for you. So if you have an hybrid code and you are interested in knowing these kind of details we have presented today, please feel free to contact us or to apply from one of the services. To conclude, we have presented 2 generic approaches to characterize the efficiency of hybrid codes, and I think each of them has its own strength. As you have seen, the additive approach is keeping closer to the programming model, and this keeping closer makes easier to map to known problem. On the other side, the benefits of an abstract model is that it's more generic and that can be more flexible, adapted to any approach. And finally, the 2 models are being used in the framework of the POP Center of Excellence because we believe there is not one good and a bad one model. It depends how your brain works with the model. So the best model for you is the one that you better understand. Thank you very much.
Hello, I'm back. Thanks for that, Judith. So we're now going to try and answer your questions. If you haven't found it already, in the GoToWebinar control panel, there is a section on questions where you can ask questions. And there is also a handout section there if you haven't found that. We've produced handouts describing the additive metrics and the multiplicative metrics and how to calculate them. So I'll answer some of the questions I've got and I'll pass over to Judith. So someone asked an interesting question about parallel efficiency. Is it correct to define efficiency as the speed up divided by the number of cores, whereas the speed up is the sequential time divided by the parallel runtime? And you've probably realized that the POP parallel efficiency is not this metric. Traditionally, parallel efficiency was defined that way, and that worked very well when your smallest case was going to be running on a single CPU core. But typically now we're running on machines where there's tens of CPU cores on a single compute node, and it doesn't make any sense to compare the run on a single CPU core with multiple compute nodes, because as you load the compute node more and more, you'll get a change in behavior. So the traditional parallel efficiency, which was speed up divided by the number of cores, if you're using the one compute node as the reference case, that's only a relative measurement of efficiency. It's relative to the smallest case, whereas the POP parallel efficiency is an absolute measure of the parallel performance, because it's measuring the total amount of computation, of useful computation, divided by the number of cores. So I hope that answers that question. I've got another question as well, asking about imbalance, and is this an example of it, having 10 OpenMP threads for a loop iteration count of 15? That will almost certainly give you imbalance. I didn't go into details of how you'd calculate the OpenMP load imbalance efficiency, but the way we do it in the PyPop tool, which is a very nice tool for analyzing the OpenMP performance, we actually look for every single execution of an OpenMP parallel region. We look at the difference between the average amount of computation and the maximum amount of computation, so we can calculate then the absolute cost, and then we sum those. So in the additive metrics, the OpenMP load balance is an absolute measure of the cost of any imbalance inside the OpenMP. And I believe VTune has a very similar approach as well. Judith, do you want to answer some questions while I read some new ones that have come in?
Yeah, sure. Well, the question is if the parallel config scripts are available in the latest downloadable version, and they are not distributed, these configurations with Parallel, but with the basic analysis. So if you download the basic analysis module from the website, you will get the configs that we use to compute those metrics. Another question is about the impact of the affinity regarding to the metrics, and what was the pinning used in these examples. Well, basically, we recommend to do the pinning because it's the best approach, but this is not forced. So basically, the impact is that if there is no pinning, computation may be impacted from that, and the duration of the computation maybe have an impact on that. Another question, maybe not much related with the stock, but I can also answer, is about the size of the trace files, how to reduce them, and if there are mechanisms to focus the tracing of extract. For sure, there are some automatic mechanisms, for instance, based on the collectives or based on time, but also you can modify your sources to shut down and restart the tracing and only collect the data when you are interested.
So while you're paused, Judith, I'll answer a question. So someone's asked whether both models identify the same problems and the same value of an inefficiency for a given code, and they are fundamentally different. So they kind of approach the problem from a different perspective. So the multiplicative model tries to map problems onto the idea that you can define things as either imbalance or transfer or serialization or communication, whereas the additive model actually starts thinking about what the bottlenecks are for the software engineer if they're writing OpenMP code or MPI code, and then tries to define a specific metric for that bottleneck. So the metrics are fundamentally different. There's another question here, which I think is probably best answered by you, Judith. Someone's saying that they understand MPI communication inefficiency represents the network load and overhead. But when it comes to OpenMP, does the communication inefficiency represent barriers, mutexes, overhead?
Yeah, but basically, MPI is not the network, in fact, overhead. Basically, what we do is we compute the time in MPI. There is some waiting time in MPI that is caused by imbalance, by global imbalance, and this is blamed to the load balance efficiency. Any other waiting time in MPI that may be transfer of data or maybe temporal imbalances that compensate or may be caused by serializations is defined in the communication efficiency. And that's the reason that both models, and I do not include that in my slides, but both models then split the communication efficiency for MPI between serialization and transfer to isolate the transfer of data. In the case of OpenMP, the idea is the same. Basically, is that any waiting time inside OpenMP that can be blamed to the global load balance distributed is defined as the load balance, and any other waiting time that is not due to the global imbalance, that is basically paid on barriers or locks or idling of the threads, will be justified at communication.
So I've got another question here. Does the model support MPI applications where the computational resources assigned to a process change dynamically during the execution? I think if you can measure the useful computation and the time inside OpenMP parallel regions for each process, the model should work.
Yeah, there is no impact on that. Basically, if you have migrations on your system, what will happen is that may affect to the duration of the computing phases, like the pinning. So basically that will impact, but you are measuring, what we are measuring is when you enter and exit the parallel runtime calls. And when you are out of the parallel runtime calls, you can consider you are on your user code. And in that sense, there is no restrictions on the mapping or on the migrations that you may have.
Yeah, I suspect interpreting the data would be quite challenging if things are happening dynamically, and you might have to do multiple runs to see how the metrics, you know, if things are changing dynamically, whether they change differently with different runs.
Yeah, but let's say that you may know if your application is very sensitive and there is very undeterministic behaviors and a huge variability between runs, then it's good to analyze different cases. If you see that even there are migrations or there are movements, there is no difference on the execution time, then maybe you don't need to push math on analyzing different executions. Here I have a question about the MPI communications only between nodes. Well, again, we do not care about if the communication is between nodes or within nodes. I agree that there is one approach that tries to minimize the number of processes in the node of the MPI process and to complete with OpenMP threads to fulfill the node. But I think maybe the most frequent approach is to use one MPI run per socket. So because basically then you have the NUMA domain associated to the socket that is sharing the threads.
So another question, if code portions are using the Unix fork, how does this show up? Well, the models we're talking about today are assuming that the only parallelization are within OpenMP or MPI, but the models could be extended to look at code that does Unix forking, as long as you can generate suitable trace data. Yeah, certainly one of my colleagues looked at a case where rather than OpenMP threading, there was P threading. So I think as long as you can collect the data, you can you can start trying to generate metrics and possibly even coming up with your own sets of metrics. I don't know if you've got any thoughts on that one, Judith?
Sorry, can you repeat? I was reading other question.
If the code portions are using the Unix fork, how does this show up?
Well, yeah, extract will instrument the user fork. That will depend on the application you are using to instrument the library you're using to instrument your code. If we catch the fork, basically we will create a separate process, and that information will be included in the execution. What it may happen is that, let's say, if after halfway of my execution I do the fork, basically I will consider from the point of view of the trace that from the beginning till that point, that process was idling because there is no information. So if you dynamically a long time do forks, then you have to take care how you set the focus of analysis. If the forks are done at the beginning, then there should be no issues at all.
So another question: are there math libraries that can help with efficiency? Yeah, I mean, there's if there's a math library that does what you want, then I would use that definitely. I know, for example, Intel's MQL has multi-threaded versions of the BLAS, and there's probably other BLAS libraries that are multi-threaded, so use those if you can. They should be efficient, and you can use these metrics to compare different math libraries to actually identify which work best, or you can just run your own little experiments, try things out. Question: are there sample traces with the PyPop or basic analysis codes? There are some sample traces with PyPop. So if you download that, install that, there are some traces in there. I don't know, are there any sample traces available with Barcelona tools, Judith?
There are traces in the tutorials. There are traces with some of the tools. I do not think the basic analysis include any trace as example. We can include few of them with some basic models for pure MPI, for instance, and the hybrid. But basically, there are no examples on basic analysis, but they are examples on the tutorials and other things downloadable in the website. I have one question about how the multiplicative model will change under different scenarios for the MPI and init thread. Well, as I said, the current formulas I have explained today require that the threads, that only the master thread call to MPI and that other threads are not computed at the same time. But this is not a requirement of the mechanism, but the current formulas. So I am working to support any kind of MPI communication at the thread level. So multiple threads calling to MPI, that shouldn't be an issue for the computation of the multiplicative models in the future, hopefully in the near future. Another question is about the measurements if we use standalone runs, and if what happens, what is our experience when we try to optimize a code using a multi-user HPC environment. Well, that's really a mess, because basically, if you are sharing the resources within a node, or if you are sharing part of the nodes you are using, the problem is that typically that may generate imbalance in your execution. So if you try to optimize one code that is being sharing the resources with other jobs, is really a mess, because the requirements from the other jobs may be changing a long time. So you will need to have dynamic mechanisms to adapt to the resources you have available. It may happen, for instance, that you are running at the same time with a process that requires a lot of memory, and then you are running out of memory. It depends if you are sharing the socket, or let's say if the other guy is sharing your socket, is only sharing your node, or is only sharing the traffic in the network, okay? But for sure, if you want to make it a good analysis of your code, it should be running on a standalone. You can get the information. There is no restriction to get the information and the metrics, but then basically it will blame, because those efficiencies are basically not specific for a program, but for an execution of a program. So it's the hardware and software and your application, the ones that define these timings. So basically, if there is extra processes running, you may get different efficiencies on each of the runs. About extending the model with OpenMP and CUDA, well, in fact, I have been looking at one example. I didn't have a look on OpenMP and CUDA. The benefit of the multiplicative, as I said, is that I am not considering any restriction we respect any specific constraint from any programming model. So if I can keep abstract, I can apply to MPI plus OpenMP plus CUDA or to OpenMP plus CUDA. The only requirement is that I need to be able to split between the different programming models. In the case of CUDA, it's quite simple, or let's say it facilitates the process because basically CUDA is mainly executed in a different device, in a different, in the GPUs, it's not in the CPUs. But for instance, there will be limitations if I try to instrument and split between OpenMP and pthreads. That in fact is a model that is not supported by Extrae because OpenMP threads are implemented based on the pthreads. I think it's time to conclude this.
Yep, okay, well, thanks for listening. Just a reminder that there's a lot of resources on the POP COE website, and this webinar has been recorded, so you'll be able to listen to it again if you want. And there's the handouts, which you can download now, which are on the website. And if you do need help assessing the power performance of your code, then please apply on the POP website for one of our services. These are funded by the European Union, so services we provide are free. And thanks for listening.
Thank you.